This is a demonstration to illustrate the use of DCR choreographies to specify the behavior of heterogeneous swarms in TaRDIS. DCR choreographies are one of the chosen event-based programming models to specify the behavior of heterogeneous swarms in TaRDIS. The main idea is to use a DCR choreography to specify the global behavior of a swarm and by means of a compiler generate code to execute in the participants' devices and execute their local behavior. So DCR choreographies are also amenable to verification and verification of properties like confidentiality. So let's take an example. So we take inspiration on the energy communities use case of EDP, and we consider three participants, three prosumers, one producer, two consumers. P0 is a consumer, an electric vehicle that will be needing energy in the next hour. P1 will be a house with a solar panel, which is able to produce energy in the next hour, and P2, a house equipped with batteries that will also be able to provide energy in the next hour. The DCR choreography that specifies this example is the one in this slide. So what we have here is a depiction of a series of events. So events are the basis for DCR choreographies. So DCR stands for dynamic condition response, and the words condition and response are the names of relations between events. So these yellow arrows between events like the consume event in the center and the reply events on the right hand side are condition relations. So we have events and we have control flow relations that shape the way that these events can happen. On the left hand side, we have what we call computation events. Computation events store data, or they compute and store data. So on the right hand side, then we have input and interaction events, which represent interactions with the external context, user input, sensors, etc., and interaction events that also signify messages between participants in the swarm. We can see, for example, in the computation events, we only have P0, P1, and P2 listed on the top of each one of the events, meaning that they are local events. They do not have anything listed on the bottom side of the box, which means they are local to each one of the participants. On the other side, we have a consume event that goes from P0 to P1 and P2. P1 and P2 are listed at the bottom of the box in the choreography. This means a message is sent from P0 to P1 and P2. So important in DCR choreographies is the notion of enableness of events. So condition relations, the arrows between these arrows between the events, represent a causality between these events. So the reply events can only happen after a consume event has happened. So looking at this choreography, we can deduce that the only enabled events are the computation events and the consume event, because it doesn't have any condition going in. So we need to first execute the consume event in order to be able to execute the reply event. So in this case, if P0, the consumer of energy, executes the event consume by interacting with the system, so it enables the event's reply from both P1 to P0 and from P2 to P0. So there are two instances of the event reply, each one assigned to one of the participants, P1 and P2, the producers of energy. Same happens when P0 executes the event reply, sends a reply to P0, then P0 can execute an accept or reject event. Same happens in P1. If P1 executes reply and sends a message to P0, then P0 can send a message accept or reject back to P1. So in this case, there is no restriction on whether I can accept, reject, or both. So we also include other kinds of control flow relations between events, and this red arrow represents an exclusion of an event. So an explicit exclusion of an event from the choreography. So an excluded event is no longer enabled. In this case, if P0 sends an accept message to P1, then it excludes the reject event from the choreography. And on the case of P2, P0 executes a reject event, so it will exclude the accept event sent from P0 to P2. What we can see now is that the events accept and reject and also reply are still enabled and can be executed again. It makes sense to add an exclude relation from reply to itself and from accept to itself and a reject to itself, meaning that these events can only happen once. So these are two basic relation conditions that specifies that one event happens after another, and the exclusion relation, that is a relation that has an effect on the state of each event by including or excluding it from the choreography. So these are two kinds of relations. Of course, DCR graphs, and in particular DCR choreographies, have other kinds of relations like these ones. So the include relation, the dual to exclude, explicitly includes events into the choreography that are there but are somehow excluded or start excluded. The condition relation that we have already seen, and the response relation that by executing an element or an event on the left makes the event on the right hand side mandatory in this process. So the notion of mandatory events is not here central to the example. We also have the spawn relation, which is the relation that we use to create new events and expand the choreography. Also not illustrated in this example. What we have seen so far is the visual representation of a choreography. In our prototype, we use a textual representation seen here on the right hand side, where we declare the events and their relations in a fairly one-to-one relation with the diagram. So we then take this textual representation, use a command line compiler and the usual tools like Maven and Docker to produce Java code that runs on separate nodes in the network and make the choreography work in a decentralized way. In the future, we will have a visual representation, and we're also planning to have online reconfiguration of these choreographies. Going back to our example, the architecture that we are about to show in this demonstration is this. So at the bottom, we have the Babel communication framework that offers reliability, security, and some correctness properties of the communication. On top of that communication framework, we install 3 nodes in a network of swarm participants. Babel offers a communication stack, and on top of that communication stack, we install a coordination app that offers us, in a simple HTTP interface, a REST interface to devices, the capability of triggering events to execute actions in their choreography. So only the enabled events are available at that interface at a given time. So the vision for this demo and for TaRDIS in general is that on top of this DCR coordination app, there is a decision and control app that links to the device and uses some AI mechanisms to decide which actions to take at a given time. So for instance, in this case, we have an electric vehicle that will have an ETA of 1 hour, and it will consume 30 kilowatts in 1 hour because it needs to charge. So the control app can communicate to our choreography that it wants to consume an amount of energy in a given time. We also have the house with the solar panel and the house that contains a battery, both producers of energy, and whose control and AI decision app may decide to reply to the requests of the consumer and state that they will be able to produce the needed energy in the given time frame. We will now show you the actual demo with a Babel infrastructure and the DCR coordination app working in communication with 3 nodes. What I'm going to show now is the instance of our architecture where we have 3 devices, in this case 3 iPhone simulators, connected to the DCR coordination app in each one of the participants for this demo. So an electric vehicle, a solar panel, and a battery. So the interaction of the device would be the one I will simulate in this application here, which is only a web application connected directly to a Babel instance. Okay, so let's move on then to our example. So we have here the description of our example in a textual format, which we then go through a phase of building. So we translate this example into Java code, which produces Babel Java classes to be integrated in a Babel application that contains the communication stack. Then just build a Docker image that represents the participants in the choreography, and by launching each one of the instances, giving it a name, in this case P0, mapped onto port 1, 2, 3, 4, P1, and also P3, we now have 3 Docker instances, each one mapped in a different port, which means that our applications here can now be refreshed, and because they lost the connection, so they can be refreshed, and they are all connected to ports 1, 2, 3, 4. Just by connecting them to different ports, we can have different views of the choreography. So let's look at this and connect to 1, 2, 3, 6, and zoom out. Okay, so now we have an electric vehicle that has available the consume event. A house with a solar panel doesn't have any event available, and a house with a battery which doesn't have any available event. So in this simple process, so if I just say that in the next 60 minutes I want 30 kilowatts of energy, and this would be triggered by the device itself, by the car arriving to a certain position, so I can see that the reply consume for P1 and P2 become available in both the house with the solar panel and the house with the battery. So, and I can say that, okay, in the next 3 hours, I can give you 100 kilowatts because it's what I have. So now, in the case of the electric vehicle, it becomes available. I can now have the accept and reject events available. I can already accept it, or I can wait a bit more, and okay, the battery will give me 45 kilowatts in the next 2 hours, which is fine. And then, of course, then I have the accept and reject for each one of the offers that I got. So I can now accept P2, which then disappears the reject, as we have programmed with the exclude relation, and I will reject P1, and I'll reach the end of this process. Of course, I can now program the choreography to have more consume events being triggered and start again. But this is the simplest process we can demonstrate for real, running in 3 Docker instances with an architecture that follows the TaRDIS managed services idea.